Hello, in this video I want to look at the limit comparison test. So we actually looked already at a direct comparison test of which we found that it works for most but not for all. So in any case, for example, we would have to consider two sequences of which are non-negative, and this will be for all n greater than or equal to 1. Now basically what we have is that if, for example, we take the limit as n approaches infinity of, let's say, an over bn, and it equals L, or it fails to exist, then you have that the series of an and the series of bn we'll say it like this, okay? So we'll say that it will converge or diverge. Okay, that seems a little strange, but in any case, it's no worries because we can actually show that, for instance, in using a limit comparison test, that we can find, what a sequence or series might do. Series, yeah. So if you watched the previous video about the direct comparison test, you might have seen that we had n squared minus 1, and this was from n equals to 2 to infinity. Now, of course, in any case, what is an? An is 1 over n squared minus 1. But then that means that bn would be something comparable, so like n squared. Now, of course, what do we know about 1 over n squared? Well, basically, it's a converging p-series. So we have that it converges by p-series, and what do we need to do? Well, we have to take the limit as n approaches infinity of an divided by bn, which, if we go ahead and we apply that, it's basically just going to give us n squared over n squared minus 1. Now, essentially, we have that if we apply the limit operator, it's going to be infinity over infinity. But one thing that we could do is just say, well, just divide that by n squared on top and bottom, and in any case, that would give us the limit as n approaches infinity of 1 over 1 minus 1 over n squared, which in fact would equal to 1. Now, okay, well, this limit value over here, it has to be real and finite, so in any case, we have that this number 1 is a real number, and because we compared it to a converging p-series, then we can furthermore just conclude that that by the limit comparison test, that the series of 1 over n squared minus 1, it converges. Now, if I was going to, let's say, for example, use the integral test, you would basically find the exact same thing. You would find that that's a series that converges, which, I mean, that may be a little bit more involved if you think about it. Okay, now, another example that we could look at is, what if we had 1 over the square root of n plus 1, and let's say that this is from 1 to infinity, okay? So I know what an is. An is equal to 1 over the square root of n plus 1. Bn would have to be something comparable, which in this case would be 1 over the square root of n. But in any case, I have that this is a diverging p-series. Okay, so this diverges by p-series, and just for clarification, that's 1/2, which is less than 1, which would mean that it diverges. Now, okay, so what comes next is that we just have to look at basically the ratio of their sequences. So we would have the limit as n approaches infinity of, well, notice that in any case you have 1 divided by the square root of n plus 1 divided by, well, I'm going to write it like this, 1 over the square root of n, which is the limit as n approaches infinity of the square root of n over the square root of n plus 1. But notice that in any case, this is actually interesting because you have that you can rewrite it as the limit as n approaches infinity of n divided by n plus 1, which in this case would be the square root of 1, which is 1, which is a real finite number, of which that you can then furthermore say that this series 1 over the square root of n plus 1, it diverges by the limit comparison test. So in this case, we just needed to compare it to something, right? Okay. Now, if, for example, that we were to consider, like, let's say, for example, a similar series, if you will. So, like, for example, like if we have the series summation of 1 divided by the square root of n squared plus 1, and this is from 1 to infinity. Note that in either case, what is the an? The an is 1 over the square root of n squared plus 1. But what is bn? Well, bn has to be 1 over the square root of n squared, which is equal to 1 over n. Now notice this though, okay? We have that basically the 1 over n, this is a divergent harmonic series, or you could just say the harmonic series, whichever that you prefer. And I think I said in class once that if you ever forget, you can always just use p-series, right? And that it diverges. So, well, we said that it basically would have to be a diverging series, right? The comparison. So basically what we're going to say from here is that the next step is that we would just have to take the limit as n approaches infinity of, now notice that it's going to be 1 over the square root of n squared plus 1. So in either case, I mean, it's basically just n, right? Divided by the square root of n squared plus 1. And the easiest way that we can do this is by factoring out an n squared, which means that you have the square root of n squared, and this will be the square root of 1 plus 1 over n squared, which in either case, that's the limit as n approaches infinity, and you have n over n, and that's 1 plus 1 over the square root of n squared. Okay, now, but notice that the n's cancels out. Okay, so once the n's cancels out, you can see that basically that you're taking the limit as n approaches infinity of 1 divided by 1 plus 1 over n squared, which actually has to equal to 1. So what we can conclude is that the series, so we'll do it like this, we'll say that the series of 1 over n squared plus 1, it diverges. Keep in mind that it diverges because you compared it to a harmonic series, and those harmonic series, they diverge, of course. Now, one thing that we can look at, for example, is, okay, well, I can utilize the limit comparison test multiple times if it can be used, or if it's like, one of those tests that, we want to use, that is. Because, some of these that I have done, they are easily shown by integral tests. Okay. But like, let's say like, you have a classic, you have a classic of 2 divided by n times n plus 1. Now, in either case, this is interesting because essentially you could rewrite this if you needed to, but you really don't have to be honest, and that's going to be 1 over n times n plus 1. Because basically what we're seeing is that essentially we can say that the an, okay, so we could say that the an is 2 divided by n plus 1. But what is bn? Bn could be, for instance, just 1 over, well, if I remove the 1, then in that case, that's just going to be n squared. But, okay, so that means that the series of 1 over n squared, it's essentially a converges by p series. Okay, so we have that converges by p series, the 1 over the n squared. But we still would have to actually work out the process of, taking the limit, okay? So we have take the limit as n approaches infinity of 2. Now, what we could probably do here is just, write 2n squared divided by n times n plus 1. Now, in any case, this is infinity over infinity, so we could probably just divide everything by n squared. So we divide everything by n squared, and this is going to equal to 2 divided by, well, basically that's n squared over n squared, which is 1, plus 1 over n. Now, in either case, we're saying that if we take the limit as n approaches infinity of 2 divided by 1 plus 1 over n, that this is going to equal to 2 over 1, which equals to 2. So that means that basically by the limit comparison test, that we have that the series of 2 divided by n plus 1, it converges by the limit comparison test. But we could have technically had used the sequence of partial sums because this represents a telescoping series. But also, you could have shown using the integral test, and you would have probably got the same thing. But I guess what I'm trying to say is that it doesn't really technically matter as to what the series converges to, in the sense that we already know, that basically your only interest is really just showing the convergence, actually. So we kind of just omit that part in terms of what is it converging to, that is. And you would find that you wouldn't use it for all necessarily. For instance, if you have basically the series of 1 over 2 to the n plus 1, you wouldn't necessarily say, let's go ahead and use this for a limit comparison test to show that it converges. But it wouldn't be a bad idea because, what would you compare it to? You would compare it to 1 over 2 to the n, which basically this is a converging geometric series. And, technically you could probably, I guess, integrate this using, you can use the integral test, actually, probably. Yeah, that probably would be okay to go ahead and use the integral test. But, like I said, it's going to be probably dependent on what you prefer and what's the easiest thing. But technically, you would not use a limit comparison test. But if you did, it would show convergence. But I think that what would suffice is probably a direct comparison in actuality. Okay? So limit comparison test, in a sense, is a little stronger, and it's going to show whether or not a series converges or diverges, but it requires that you do know, the basics, that is. So I'll just leave you with that you can try, for example, a series that you can write as n squared plus 1 divided by n to the 4th plus, let's say plus 2. So if this goes from 1 to infinity, you would just have to think, what is your comparison in this case? And I'll give you a hint. It's the series summation from n equals 1 to infinity of n squared over n to the fourth. Once you reduce this, then from there you will be able to determine whether or not that series that we are comparing it to is convergent or divergent. But it would require that again, that the series will either converge or diverge by one of the tests that you have learned so far.